We're now going to learn how to build models. The first technique that we'll use is linear regression. Linear regression is the most popular and one of the oldest techniques for building models. It's highly interpretable and relatively easy to implement. In sciences, it works well since it can model sinusoidal, linear, and polynomial relationships. It's also used extensively in econometrics because it's easy to interpret the various effects. Suppose in our data set we have n data points. We have one response or output value and p other predictors or input values. Then simple linear regression assumes that the relationship between the ith response yi and the ith predictor values x1i, x2i, x3i and so on is of the form as shown. So overall, the response vector y is related to the predictor vectors by the equation shown here. Essentially, the response is assumed to be some linear combination of the predictors. The method works first by deciding a cost variable to minimize. In this case, we usually take the residual sum of squares. Remember residuals from last time? The difference between the predicted value and the true value is called a residual. It is simply the sum of squares of all the residuals. Now, the algorithm tries to reduce this cost function by arbitrarily choosing initial values for the parameters beta 1, beta 2, and so on, and then tuning the parameters until a minimum cost setting is achieved. This idea is called gradient descent, as the algorithm descends the gradient of the cost function, which in this case is the residual sum of squares. Once you've built the model, it's important to know how the model performs. We use two metrics to judge this. The first is R-square. It's a measure of how much of the variance of the output is explained by a given model. Its value lies between 0 and 1. The higher the value, the better. The other metric is the correlation of the predicted response and the actual response. It again lies between 0 and 1. Very good R-square or correlation, say greater than 0.7 on training data, and very poor on test data, say below 0.2, is a sign of overfitting, as discussed in exercise 2a. For an idea of how to get these two metrics, please see the link provided here. Sometimes you may not know what predictors are important, or there may be too many predictors to manually decide which of them are important. In this case, we use automated feature selection. Ideally, one would like to try out all possible models. However, this is unfeasible, since for p predictors there would be 2 to the p models, and this exponential model space cannot be efficiently searched. Even for 10 predictors, it is impossible to go through all possible models. Instead, we use other strategies. Two of the most popular are forward feature selection and backward feature selection. In forward feature selection, we add the most significant feature, then add the second most significant feature, and so on until the model does not improve significantly or we hit some pre-decided number of features. In backward feature selection, we start with a model containing all the predictors and then recursively remove them until removing any predictors significantly decreases the accuracy of the model. Not all the data we work with is the same. Sometimes you have categorical data. Data that says if a data point belongs to a particular category. If there are only two categories, 0 and 1, then a simple linear regression on this variable works well. However, if there are multiple categories, this type of data cannot be fed into the regression as is. It makes no logical sense to treat the different categories as ordered in some particular way. What sense does it make to say that increasing a category by 0.2 increases a variable by some amount? In this case, the variables must be treated before putting them in the regression. There are various strategies for doing this. Using dummy variables is one of them. For each category, we create a variable and assign a data point as 1 if the data point belongs to that category or 0 if it does not. Thus, for a predictor containing 5 categories, we would end up having 5 different new variables, and each data point would have a 1 in only one of these 5 and a 0 in the other. For more information, look at these two links provided. The more important part of any fitting exercise is making sure that your assumptions are correct and improving models as you build them. Even for a simple technique such as linear regression, there are several pitfalls you can fall into. The first is that the true form of f is not linear. You can find this out by plotting the residuals, that is, the difference between the true response and the predicted response, versus the fitted values for the response. If the errors don't seem to be randomly distributed or belong to the normal distribution, then there is a problem. For example, in this plot here, clearly the residuals seem to be fitted to a quadratic polynomial when plotted against the fitted values. This was a good hint to try and fit some other type of polynomial instead of a simple linear fit. So, after a quadratic fit was made, the new distribution of residuals versus fitted values seemed much more random. A second common pitfall is collinearity. Collinearity between predictors is a problem because if two predictors are highly correlated, then the least square solution is not stable, since there are multiple equally good answers that have very different weights for the two correlated predictors. This makes it likely that the model will perform poorly or unseen data, or in extreme cases, even end up returning random values for any model that you build. Another common problem is the existence of outliers and influential points in your data. Outliers are points that have dramatically different y values than other points with similar x. This is an example of an outlier. Here we see that this point has a very different y value from other x values. Points of high leverage or influential points are points that don't have corresponding points that are similar x values. This is an influential point. High leverage points affect the regression equation, and they can make the relationship seem very different from what it really is. Outliers make the error terms of a regression much higher than they actually are. Both of these points either need to be removed or dealt with by techniques such as robust regression. We'll now move on to the exercise, where we're modeling Boston housing data. We have data for different suburbs of Boston and several other characteristics for them. This is the same data that you saw in the last exercise. We're now going to try and build a predictor using the values that we have. Best of luck.